Dear fellow scholars, this is a new episode with a special guest. Today we are going to see how a sensor that seems to defy gravity has just unveiled one of the most important secrets of our universe, dark energy. This new result comes from the most precise measurement of our universe's expansion to date, and it is nothing short of spectacular. So let's have a look. This experiment sounds like science fiction. A sensor that seemingly defies gravity and can move freely in all directions without any forces acting on it. But it is real, and it works by making use of one of the most precise atomic clocks ever built. You see, the key to this miracle is that this clock is not just ticking away time as usual, but instead it keeps track of tiny changes in the positions of its atoms. And these changes are not random at all. They follow an incredibly regular pattern, which makes them incredibly predictable. This means that we can use them to measure small changes in the very structure of space itself. So here's how it works. First, the sensor is placed inside an evacuated tube. Then a laser is carefully aligned so that it points at one end of the sensor. Now, if the sensor were not moving, then the light would just reflect back from the far end. But the sensor is actually moving in a regular pattern. And this changes the frequency of the light as it comes back because the light has to stretch or compress a little depending on whether the sensor is moving towards or away from it. This way, the motion of the sensor atoms is converted into a change of frequency of the light. This change of frequency can then be measured incredibly accurately. And from this, we can infer how the sensor has moved. But why does this work? Why does the sensor seemingly defy gravity? Well, remember that according to Einstein's theory of general relativity, space and time intertwined in a four-dimensional fabric are not absolute, but are woven together in a very particular way. They depend on where you are, and more importantly, they depend on what mass is around you. For instance, if we put a massive bowling ball onto this trampoline, then it will warp the trampoline cloth and cause it to sag. In the same way, a massive object warps spacetime, which means that the position of the trampoline and the bowling ball relative to each other changes over time. That is, they fall towards each other. But since the trampoline cloth is stretchy in all directions, the bowling ball doesn't just fall down, but rather it falls towards any location on the trampoline. It's always the shortest path to the ball, and spacetime works much the same. Massive objects make spacetime sag, and other objects then move along the shortest path. Through this curved spacetime, we call these paths geodesics. And it is those paths that we usually mean when we talk about the path of a planet or star, or black hole or anything else. Now, the thing is that these paths are not straight lines. They curve around massive objects. So the question is, if we send out light, say from Earth, in a straight line, then what path would it take through curved spacetime? Would it still go in a straight line? Well, yes, but only approximately. And that's the key to understanding how this experiment works. You see, the light has two choices. Either it follows a geodesic and curves around the sensor, or it goes straight. The latter is, however, impossible if there is no bowling ball. But if we add a bowling ball, then it becomes possible. You see, the light can now go around the sensor and arrive at the detector slightly earlier. And this is what happens in the experiment. If we remove the bowling ball, then the light takes the curved path and arrives at the detector at the predicted time. But if we add the bowling ball, then the light has the option to take the shorter straight path, and it will arrive at the detector earlier than predicted. And this is what they've measured. The tiny change in arrival time of the light tells us how much the sensor has moved during the time of flight of the light. And this is how they can measure the motion of the sensor atoms incredibly precisely. But what does this have to do with dark energy? Well, the acceleration of the expansion of our universe is supposedly one of the major effects of dark energy. If we want to measure this, we need to know how fast the universe was expanding in the past. And for that, we need to measure the distance to very far away objects and also find out how fast they are moving away from us. And this is what this experiment now makes possible. They can measure the distances to supernovae 10 times more precisely than previous experiments. With this unprecedented precision, they've looked at supernovae at distances up to 9 billion light-years away, and they found that the expansion of the universe has indeed been speeding up as expected. But they also found something else, something unexpected. It's this. There seems to be some sort of tension between the results of this new measurement and that of other measurements we have made recently. This could be a hint that our models for the acceleration of the universe are wrong. Or it could mean that our models are right. But something is wrong with this new measurement. You see, there are several ways to measure the acceleration of the expansion of the universe. One way is to measure the light from supernovae and look at how much their brightness has changed. Another way is to look at the cosmic microwave background. And yet another way is to look at the abundance of light elements. And each of these measurements gives a value for the so-called equation of state of dark energy. And that's this W. The value W equals -1 would mean that dark energy is a cosmological constant. The current value of this W agrees with that of the supernovae measurements. However, the value from the cosmic microwave background and that from the abundance of light elements disagree with both of these. This apparent disagreement could mean that our theoretical framework needs some updating. Maybe dark energy isn't just a cosmological constant, but rather it changes in time. Or maybe it changes in space, which means that it wouldn't be a constant. For all I know, it could also mean that something is wrong with one of the experiments. Maybe something with this new one, or maybe something with the supernovae measurements. What do you think? Let me know in the comments. And either way, this is a spectacular achievement, and it shows how creative humans can be in their quest for understanding the fundamental laws of nature. By the way, this experiment was done by the NPL in the UK and the University of Colorado, Boulder, and JPL, California Institute of Technology in the US. They used one of the most precise atomic clocks ever built, which is located at the NPL. They developed the quantum sensor together with scientists from Sandian National Laboratories in the US. The data analysis was done with the help of the NASA Datenbank Cosmo in the US and the HT, the supercomputer at ZIP in Germany. And the experiment was funded by various organizations, including STFC, Science and Technology Facilities Council in the UK, the European Space Agency, and NASA. Thanks for watching. See you next week.